Alrighty, this warm-up is a bit of a review from what we went over with the Edpuzzle video the other day. So how many degrees does each interior angle measure for a regular dodecagon? So a dodecagon here, there's pictures given to us here, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 sides. So we need to use our formula to find the measure of each interior angle. That formula was 180 times n minus 2, n being the number of sides, divided by n equal to our interior angle. We just call that A. So we just need to plug in n here, n being 12. So 180 times 12 minus 2 over 12 equals A. And so we need to subtract first 180 times 12 minus 2 is 10 over 12. 180 times 10 is 1800 over 12. And so that gives us our A. So that comes out to be 150 degrees. So there we go. So now that we have that, let's go ahead and review this stuff a little bit too, because we're going to need to use this here in a minute when we start to look at area of these figures. So first things first, today's topic is all about area and perimeter of regular polygons. So by the end of the lesson, you'll be able to develop a formula for the area of a regular polygon and solve problems using the perimeter and area of regular polygon. So first up, a little bit of review of what we saw in our Edpuzzle video. First off, the formula for sum of all of the interior angles and exterior angles as well. But the sum of the exterior angles for every polygon is 360. Even if it's not even a regular polygon, it's still 360. And same, really the sum of all of the angles is going to be that number, whatever it is, no matter what, if it's regular or not. When it does matter if it's regular is if you're looking for each angle. And once you start to divide by n there, it has to be a regular polygon. And you even have two different options for the formula for each angle of the interior angles for a regular polygon as well. This little table here helps you get through the first 7, 8, yeah, 8, 8 different figures from a triangle all the way up to a decagon, ignoring the one-sided and two-sided because that's not a thing. But from a triangle, square, pentagon, hexagon, heptagon, octagon, nonagon, and decagon, the sum of the interior angles and the amount of each interior angle are in the table for you. So some important terminology. The outside circle. So what is going around the outside of the polygon? We saw this when we saw triangles as well. It's called the circumcircle. And then from the center of the circumcircle to the edge of the circumcircle is the radius of that circumcircle, and that is also going to be the radius of the polygon, because it goes from the center of the polygon to the vertex, which the vertices all are intersecting the circumcircle. And then we have the incircle there. Again, we saw this when we saw triangles. The incircle is the circle inside of the circle is called the incircle, and it just touches each side of the polygon at its midpoint. Only, of course, if this is a regular polygon we're talking about here. So here we have the radius of the incircle is the apothem, because it goes from the center of the incircle, which is also the center of the circumcircle, to the edge perpendicular to the edge of the polygon. And of course, if that is true, then it also is going to intersect with the incircle as well. Just some ideas as to where those things come from. And we're going to notice here that that's going to make a right triangle. We're going to use that right triangle to our advantage here in a moment. So breaking this down into triangles here, this is what it looks like. And notice we have the same triangle several times, right? The radius there is going from the center to each vertex. splitting this hexagon, for example, into 6 similar, not just similar, congruent triangles. So 6 congruent triangles. And once we know that, we can find the area of each triangle and multiply by the number of triangles we have, which is the same number as the number of sides that we have. And remember, finding the area of a triangle is just finding the height times the base and dividing by 2 or multiplying by 1/2. So that's basically what we would do to get the formula here. So let's look at this real quick. So the apothem and the side. So the apothem here is also the height of the triangle. Helps if I spell triangle right. There we go. And then our side length, of course, is the base. So side is equal to base. So remember the formula for the triangle, area of a tri is equal to 1/2 the base times the height. So we replace the base with the apothem, and we replace the height with the apothem, the base with the side of the triangle. So the area of the polygon will be the area of, or that area of the triangle times 6, right? So that, let me rewrite this. So the polygon is the area of the triangle times the number of sides, which is n, right? That's what we've been using as that number. So we just plug that in. So 1/2 base times height, but swapping base with the side length and swapping the height with the apothem. The apothem times the side length times the number of sides. This part right here, though, is something special. The number of sides times the side length is the perimeter, right? If you have one side and they're all the same, you multiply that times the number of sides we have, that's your perimeter. So our area of a polygon is 1/2 the apothem. The apothem times the perimeter here. So the area of a polygon is 1/2 the apothem times the perimeter. Now, if you're given the side length and you're given the apothem, that makes things much easier for us. We can just multiply this stuff out and get our answer. Doesn't always work out that nicely, and we'll see that here in a moment. Now, before we do that, though, let's just take a look at some pictures here. So polygons used in computer graphics. So notice here that they have these polygons that are getting smaller and smaller and smaller, which means there's more and more and more of them. And you get more and more detail the smaller and smaller the polygons get. So the more the merrier, right? The more detail you get. So it used to be like it looks like on the left, and now it looks even more like it does on the right. Probably even more detailed than that now. So here is that formula we just came up with. The formula of a regular polygon. So your next problem here that you're going to give it a try on is a pentagon. You're given the two things that you need. Not exactly the perimeter, but you can find it. And in a moment we'll come back and take a look at it.